You should have done 7.4 today. We're going to learn about, like I said, solutions and colligative properties. Do your pre-lab. And I'll try and get all this up on Canvas again when I get home. Sapling 7.4 is where you should be as far as sapling goes. Okay, I'm just going to do it from over here, unless I have to write on the board. All right. So if you get your notes out, we'll get going on that today. All right, so as we talk about some solution properties, guys, 7.7 is where we're at here. We do calculations based on what's called colligative properties. That's properties of boiling point, freezing point, and osmotic pressure. Ions in a solution can change how things react. So when we're talking about solution properties, if we put something in a solution that will separate into ions, we count how many ions that it will separate into as what we call a Van Hoff factor, an I. If it's a covalent molecule, we just count it as 1. So we'll talk more about that in a minute. So we have electrolyte and non-electrolyte. Electrolyte will carry a charge through it because of the positive and negative sides of the ions that are in there. So here is the colligative properties. They are boiling point elevation, meaning it's going to go up if I put something into a solvent. If I put a solid in a solvent, the boiling point will go up. Freezing point is depressed, it will become more negative. Vapor pressure, meaning how much will go into gas, will be lowered. And osmosis is possible, meaning that water or particles will pass through a tube that has holes in it, like the dialysis tube that we're going to be using. I can go back. We're going to talk about each one of these 4 a little bit more in depth, so we will hit each of them again. So if you can get all of them written down, we will be hitting each one. A non-electrolyte is one that doesn't have a positive or negative charge. It would be a covalently bound molecule. Okay, so think of it like an alligator jar. A boiling point will go up, freezing point goes down. As we work with this, we use this equation right here. Notice that the boiling point and the freezing point equation are basically the same except for the Kf or Kb. For water, Kb is, and you barely can see it, I don't think you can see it on yours. The Kb here is 0.51 degrees Celsius per molal. And over here, the Kf is a negative 1.86 degrees Celsius per molal. And remember, the I is a Van Hoff factor. That's how many particles will it break into. So how many ions, or if it's not ionic compound, just a covalent compound, the I would be 1. Molality, you remember I told you we were going to be talking about a lot of different M's and concentration. Molarity was moles per liter. Molarity, molitery, molarity, molitery, molarity, molitery, moles per liter. Molality, I have to think, it makes my mouth go fat, so molality, I think fat, so it's moles per kilogram. That's the only way I can remember which one's which. And molality is an italicized lowercase m. Okay, so this right here is molality, which is, like I said, a lowercase italicized m. Again, one more time, if you didn't get Kb for water, it's 0.51 degrees Celsius per molal. And the freezing point constant for water is negative 1.86 degrees Celsius per molal. And we'll be using this equation a lot. 0.51 degrees Celsius per molal. So you can sort of see on this phase diagram what happens when we get a solvent. We move the boiling point and the melting point lines. So for every single thing that we have, it will have a different K. So for water, we talked about, I believe we said, yeah, 0.51, and then we used a negative here. Now, oftentimes Ks are not given with a negative, but if you remember that freezing point is depressed, it's going to be lower. If you put a negative, you know what's happening there. So that's what's going on there. So, and you always have to know about what the normal freezing point is for water. And when they say normal, all that means is going across on the phase diagram at 1 atmosphere. So vapor pressure lowering is one of the other colligative properties. That's when not as much will go up into vapor. So with a pure solvent like right here, we have a lot of it going up into vapor above the liquid. Or if you have a closed system right here, you have a lot of it coming up into vapor above the liquid. When I add a solute, it sort of blocks some of that solvent from coming up into vapor. So we actually end up with a lower vapor pressure, or not enough. If you're in a closed system, it doesn't have enough pressure to push the liquid up. Then we get to osmotic pressure. Osmotic pressure is this equation right here, which is basically perv-nert. Okay, this symbol is P, but it's more often written as like a capital pi. But it is pressure, so that would be P. And capital M is moles per liter, so that would be N and V. So remember it was PV equals nRT. So we just brought the V from this side to this side, and we've added the I. The I is just how many particles. And basically what osmotic pressure does is it allows through a semi-permeable membrane for movement from a dilute side to a concentrated side, because they'll try and get to the same. This is sort of how our kidneys work. So, and if you've ever had an IV, they have to make sure that the salinity of the IV is just right, because if it's too salty, then your body will try and go to that, send water to that area to dilute it. If it's too dilute, then it actually puts you into shock too, because then your body's trying to dilute the solution. So we have what basically is osmotic pressure, but it is basically perv-nert. Again, we have to have things in specific units. Moles, liters, R is still the 0.0821, and that's a longer version down here. And the temperature does have to still be in Kelvin, so we're still using the gas law stuff. Okay, Van Hoff factor I talked about a little bit. That is your I. That is how many particles is it going to divide up into. If it's a covalent molecule, it won't divide up, like sand, SiO2. Won't divide up because it's covalently bound. But if you have something like NaCl, it will break up into Na plus and Cl minus. Or if you had something like MgCl2, it would break up into 1 magnesium and 2 chlorines. So you have to know what how many particles it would break down into. So there's some down here, and you can sort of see what they would break down into. So we always do a whole number for I. Sometimes it's a little bit less than what we expect, but we always calculate the Van Hoff factor with a full whole number. So let's look at some examples here and see if we can figure out the Van Hoff factor. We already just talked about NaCl. What was the Van Hoff factor for it? 2. So if we look at the next one, number 2, sodium sulfate, how many ions would that break down into? Got to be careful. Remember, some groups hang together. So we've got a polyatomic here that's going to hang together, SO4. So SO4 is going to hang as a group, and Na is going to break into 2 Na. So you actually have 1 SO4 and 2 Nas. So total you have 3. Okay. The next one is sugar, and sugar is covalently bound. So because it's covalently bound, it's just going to be a 1. It's not going to break down. This is SiO2. I talked about it just a minute ago. Who remembers what it was? This is sand. Now if you look at where Si and O are on the periodic table, if you remember they're close together, and on the upper right hand side, that's covalently bound. That's two nonmetals going together. It's going to be covalently bound. So it's covalent and it's 1. Good. What about V2O5, which would be vanadium 5 oxide? Vanadium 5 oxide. How many do you think it's going to be? If we break this down into what it would come into, remember vanadium would have a +5, oxygen would have a -2. So how many vanadiums did we need? 2 of them. How many oxygens did we need? 5 of them. So total we have an I of 7. Okay. What about Cu2O? Break it down again. These are farther apart. It's ionic. So we have a copper that has a +1. We have an oxygen that has a -2, right? That's how we made that formula. So I needed 2 of these to go with 1 of those. So I have a total of 3. See how I'm doing this? Okay. I'm going to skip down to 9 and do 9 with you, but I want you to try and do 7 and 8. So let's do 9 together. So magnesium is in the second column. It has a +2 charge. Phosphate's a group that hangs together. So I'm going to have PO4 as a group hanging together having a -3 charge. And then we balanced it by using the 3 and the 2. So I have 3 of these with 2 of these. So that gives me a total of 5 for its I. Okay, really quickly, take a second and do 7 and 8. Remember, if they're close together on the periodic table, it's probably going to be what kind of bond? Covalent, which means the I is 1. Okay, so number 7, what do we get for an I? Right. The I is 1 here because it's covalently bound. Both these two are close together on a periodic table. What about number 8? Got 3. Good. The I here is 3 because we have 1 barium and we have 2 hydroxides giving us a total of 3. Okay? So let's go forward. So here we're going to calculate the boiling points of the solution at 1.5 molal. So first thing I want to do is look at the I. So on A, what's my I on A? Three. Good. I have 2 NH4s with 1 CO3, so my I here is going to be 3. So if we look at the equation for freezing point depression, the change in temperature is equal to the molality times the Kf times I, right? And we just plug in. So our molality is 1.5. Our Kf for freezing point was a negative 1.86 degrees Celsius per molal. Now remember, we put the negative there because we want to know that it's depressed, meaning it's lower. And then the I is 3. So molals will cancel and we'll end up with degrees Celsius for our unit. And go ahead and take 3 significant figures. What do we get? Okay, negative 8.37. Do I have a second on that? Okay, awesome. Okay, let's do the next one. Ethylene glycol, which, yes, sir. Yeah, we did, right here. That's I. What about what? That we use that when we're using osmotic pressure. So this is an osmotic pressure. We're going to use the freezing point depression and boiling point elevation equation, which is the delta T equals molality times K times I. Okay? So we're not, so since the freezing point of water is 0, right? I would have taken away 8.37 from 0, so I can stop right there if I put that negative there. Because 0 minus 8.37 would be a negative 8.37. So good catch. If the freezing point is a substance that has something else besides 0, then I would take that number and subtract it from whatever the freezing point was to get the new freezing point. Okay? All right, so let's go on to the next one here. Since ethylene glycol is antifreeze and it's a non-electrolyte, meaning what? What's I? 1. So I is 1. We've got delta T F equals molality times KF times I. Plugging in, we get 1.50 molal times a negative 1.86 degrees Celsius per molal. And we've got a 1 that we're going to multiply it to. And then molals go out, and we end up with okay, thank you. Negative 2.79 degrees Celsius. So you can see things that are not electrolytes do not lower the freezing point as much as things that are electrolytes. Okay, so now we're going to go to something else here where we're going to calculate both the boiling and the freezing point of a solution containing 50 grams of H2SO4, a very strong electrolyte, per 100 milliliters of water. Now, since we need molality, and molality is moles per kilogram, we need to change this to kilograms. So we're going to take 100 grams because we know water is 1 gram per milliliter, and we're going to change that into kilograms by dividing it by 1,000 grams, so we'll get 0.1 kilograms. Over here, we're going to need to change the 50 grams of H2SO4 into moles. So we're going to add up hydrogen, 2 of them, at 1.008, sulfur at 32.065, and oxygen, 4 of them, at 15.999. I believe it's close to like 98 point something. When somebody gets that added up, please let me know. While you're doing that, since it says it's a very strong electrolyte, what's my I going to be? How many ions is it going to break into? How many? 3. Good. It would be 2 hydrogens and 1 SO4. So my I here is 3. Good. Did anybody get this added up? 98 points what? 0.76. Okay. So we're going to take the 50 grams and we're going to divide it by 98.076 grams per mole. That will give us moles. So let's do that real quick. 7.7. Okay, sorry. All right, so let's divide that and get moles. .5 what? 510. Okay, that's how many moles. And remember, molality is moles per kilogram, so I'm going to divide that. I'm running out of space here on the bottom by 0.1, and that will give me my molality, which is what? 5.1, is that right? Okay. 5.1. Now we're just going to plug it into these equations. So we're going to do delta TF, and we're going to do delta TB. So for TF, we're going to take molality, which is 5.1, times it by negative 1.86 degrees Celsius per molal. Should have given myself a lot more room down here. Times by 3, and we're going to get the answer. On the boiling, we're going to take that 5.1 molal times by 0.52 degrees Celsius per molal times by 3 and get an answer. So let's do both of those. Yes. Was it 5.1? Okay, it's 5.1 then. I was just trying to remember. Thank you for keeping me straight. Anybody got delta TF done? Negative 28.45 degrees Celsius, and it doesn't write very good on the corner here. Okay, what did we get for TB? One more time. 4.6, okay. And what would we get for TB? Hopefully we don't have TB, but yeah. 7.8? 0.803. Now, since it was boiling point, what's the normal boiling point of water? 100. So we can't stop here. We're going to actually add 100 to this, so it's going to be 107. I love this, how it writes in here in the corner. 0.803 degrees Celsius is a new boiling point. Remember that since we put the negative here on the TF, we're already subtracting it from 0, so that is the freezing point, new boiling point for both of these. So this one is the freezing point, temperature of the freezing point, and this one is the temperature now of the boiling point. Okay? Everybody okay? Understand? Okay, everybody have a chance to write it down. I don't want to go too fast. Okay, going forward. Okay, for all the problems below, we're going to, the temperature is 25 degrees. Calculate the osmotic pressure of a 0.2 molar solution of sodium sulfate, a strong electrolyte. So we're going to use that equation that you talked about earlier, which was osmotic pressure is equal to I, molarity, RT. And if you just remember, it is basically the perv-nert equation, but with an I on the nert side. And you've moved the volume over, because molarity is N divided by V. Okay, so calculate the osmotic pressure of, here's my molarity. What's my I here? 3, good. 2 sodiums and 1 sulfate. What's my T? Because anytime I have temperature in Celsius and a gas law, I'm going to have to do what? Add 273.15, so it's 298.15 Kelvin, is that right? My head? Don't trust my head today. Okay, so going forward, osmotic pressure is equal to I, molarity, RT. So I is 3, molarity is 0.200 moles per liter, and I'm doing that on purpose so I can cancel it out with the R. Our R, 0.0821 atmospheres times liters divided by mole times Kelvin, times by temperature, 298.15 K. Okay, K's go out, moles go out, liters go out. I'll be left with atmospheres. What do we get? Anybody? 14.69. Okay, let's do the next one. So calculate the osmotic pressure of a solution that contains this many grams of the non-electrolyte, this urea, which is found in urine, and in that many milliliters. So what's the first thing I need to do? I got to find out how many moles, and I need to change this to liters. So that divided by 1,000 is liters, so I can do that fast. But this other one's going to take a little bit of time. I'm going to have to take a carbon, 4 hydrogens, 2 nitrogens. Is it 007? Yep. And an oxygen. And I don't have any clue on this one, so you're going to have to add that up. What is my I for this one? 1. It's a non-electrolyte, so they told me that means my I is 1. So when we get this number, whatever it is, we're going to take 95.0 grams and we're going to divide it by this number because that's grams per mole. And that will give me moles of CH4N2O. Okay, what do we got? We got the, yeah. Okay, we're going to put that here. 464.24. You can't read that. So 95 divided by 464. No, we didn't get that number. Okay, it's way wrong. Okay, give me the right number then. 60.056. Do we have a second on that? Okay. Okay. 60.056. Thank you for that. Keep me straight here. So it'll be 1 point something what? 1 point what? 58? Okay, so now we've got moles, and if we take that and divide it by liters, that's liters, by the way, then we're going to get molarity is what we need for the equation. So it should be close to 3 point what? 3.16. Now we're going to plug it into this equation right here, everything we've got. Okay. So molarity is equal to, our osmotic pressure is equal to I, which is 1, times molarity, which is 3.16 molar, times by R, which is 0.0821 atmospheres, times liters, divided by mole, times Kelvin, times by our temperature, 298.15 K. Going through and canceling, Kelvins cancel, moles and liters cancel with molarity, and we're left with osmotic pressure in atmospheres is what? I probably should have given you guys more room and me more room to write these problems out. Sorry about that. Get an answer? 77.35, we'll let it go. That's pretty strong because standard temperature, pressure is 1 atmosphere. So that's a pretty big pressure. Okay, let's do the next one. The osmotic pressure of a solution that contains 1.5 moles of calcium chloride in 1,500 milliliters. Well, at least this one's a little bit easier, right? It already gave us moles, so we're just going to divide this by 1,000 to get into liters, which would be 1.5 liters. Then we're going to take the 1.5 moles and divide it by 1.5 liters, which will give us 1 for the molarity, right? Pretty easy math here. And then we're just going to plug in. Wait a minute, I need I. What's I on this one? I hear 2. Is that right? You have 1 calcium plus ion, plus 2 ion, and how many calcium minus ions? 2 of them. So you actually get 3. So I here is 3. So plugging in everything we've got, so osmotic pressure equals 3 times molarity, which is 1, times R, 0.0821 atmospheres times liters divided by moles times Kelvin times by 298.15 Kelvin. And we end up with osmotic pressure equaling atmospheres again. And what do we get for this one? Yes? Right. Braunhilfe only when they're by themselves. If they're combined with any other element, it doesn't work. Okay? All right, so what do we get on this one? Somebody brave? 73.43. Do I have a second? Yep, okay. So not too hard. We've already done Pervnert. This is just tweaking Pervnert just a little bit. Everybody okay with this? Okay, going forward. That's the end. Yes. All right, so what we're going to do now is we've got a little bit of time. You've got computers. Work on sapling. Get up on sapling. Get your pre-lab done. Work on those things so that you're ahead in this unit. We're not going to do the lab today. We're going to start next time. It's a 2-day lab, so it'll take a little bit of time.
Where's the pre-lab on the lab?
It is, wait, oh, that's data. Never mind, there's no pre-lab. Just make sure you read through the lab so you know what you're doing before you get back there. If you have any questions, then you can ask before you go back. When we start next time, it'll be the quiz, and we're going to hit just a little bit of the notes, which is the last part of the notes, which is dialysis, and I can't even remember what it is, dialysis and something. We'll hit that fast, and then we're going right back to lab, and you've got to get your lab set up really quickly. So you need to know what you're doing when you go back there, okay? And it has to go over a 24-hour period, so we're going to actually make it go a 48-hour period. That's why we can't do it right now, because it would be a lot longer than when we need to run. 48 hours is still doubling the time that we need, but it's not 4 days. So that's why I pushed it to next week. Okay, any questions? Okay, yes? I can. Okay. Make sure that when you're finished with the computers, they get back in and put the, my brain's just left. Put the plugs back in and tuck the cords in. Yes? What? Can you what? Yes, shut the door. Yes. All right. Time's yours. Till the end of the period, please use it wisely.